Stachel is professor, it has been already said, in experimental physics at the University of Heidelberg. Johanna is one of the most prominent scientists in our field, and to most of us needs no introduction. Nevertheless, let me briefly outline the most significant stages of what is certainly a dazzling career. Now, Johanna started her studies in physics and chemistry at the University of Mainz and the ETH of Zurich, the Swiss Federal Institute of Technology of Zurich. She received the degree from the University of Mainz and also the doctoral degree from the same university in 1982. And then she moved to the US, where from 1983 to 1996, Johanna carried out her research studies and worked at Stony Brook and at BNL. In 1996, she returned to Europe, becoming professor in experimental physics at the Faculty of Physics and Astronomy of the University of Heidelberg, where she also has been the dean from 2003 to 2005. And very important, in 2012, she was elected to the very prestigious position of president of the German Physical Society. Now, in the period in Europe until now, Johanna has been involved in two experiments, mostly. First, at the in the Ceres NA45 experiment, the CERN SPS, of which she has been the spokesperson from 1997 to 2005, so nearly 10 years. For the neophytes, let me just remind you that the Ceres experiment is one of the experiments that produce the results at the basis of CERN's claim of the first experimental creation of QGP. In the late 90s, actually, there, I'm not sure, I asked Johanna, but it was 97 or 98. She also joined the ALICE collaboration. That was about the time also we started working for ALICE. ALICE collaboration, of which Johanna is one of the leading figures. She's among many things, the historical leader of the transition radiation detector project, from the original proposal to the design, construction, installation, and operation in the experiment. And she's also a member of the ALICE management board since 2000. Actually, Johanna, you are the only one who has been for such a long period of time in the management board of the ALICE experiment. Now, of course, she's very well known for her contributions to the field of relativistic nuclear collisions and the development of the statistical hadronization model together with Peter Bramunzinger and collaborators. And for her many scientific achievements and overall contributions to the field, Johanna received many prestigious awards. It would take too long to list them all, but let me just mention some of the most recent and prestigious ones. The Lise Meitner Prize of the European Physical Society in 2014. That's a very important prize, which is awarded every 2 years by EPS. The Stern-Gerlach Medal in 2019, which is the most prestigious German award for experimental physicists. And recently she was awarded the Officer's Cross of the Order of Merit of the Federal Republic in Germany, which is the only federal decoration of Germany awarded for special achievements in political, economic, intellectual, or honorary fields. So, as it has been already anticipated, today Johanna will give a seminar entitled Experimental Constraints on the Phase Structure of QCD from LHC Data. So now, without further ado, I will give the floor to Johanna.
Okay, thank you very much for the kind introduction. Actually, I would appreciate a lot if some of you could keep your cameras on, that I could look into some faces. I can't see more than 4 people at the time. So I see Luciano, Tatjana, Edward. I could use one voice because it is really, after at Cork Matter, we started to appreciate how nice it is to look at people into faces. And yeah. Okay, so my plan right now is to really coming from an experimental side, except for very few introductory slides, to tell you where we are constraining the phase structure of QCD. Of course, with the LHC, we do this at net baryon density very close to 0. But I will make some remarks also where appropriate on excursions into larger net baryon density. I will start in terms of observables with hadron yields, and then make a few comments on net charge fluctuations, both in the grand canonical and canonical ensemble. Then I will move to Charmonia and open charm, and first discuss evidence for thermalization, and then what we can do about production of charmed hadrons. And then I think today there will also be time to still make an excursion into the beauty sector. So I think to all put us on the map, this is the beautiful accomplishment by our colleagues in Lattice QCD on constraining the chiral phase transition. You see here, the picture is from the Hot QCD collaboration, where they take several measures, among them the derivative of the chiral condensate, to come to a pseudo-critical temperature for the chiral crossover transition of 156.5 plus minus 1.5 MeV. And below you see the number that was published in 2020 from the Wuppertal-Budapest collaboration, 158, with an even smaller error of 0.6 MeV, but in complete agreement. It is more difficult to come to an unambiguous signature of the deconfinement in lattice QCD, because there is no order parameter for finite quark masses, but it was suggested already in 2006 by Echiri, Fridtjof Karsch, Krzysztof Redlich, that one can look at the quark number susceptibilities, and in particular the ratio of the force derivative of the pressure with respect to chemical potential divided by the second derivative is proportional to the baryon number squared. And of course, that is 1 in confined matter, and this value becomes 6/9 pi squared for deconfined matter. And you see here the very rapid drop coming again from the two lattice QCD collaborations, but also a result from using the functional renormalization group. And as you see, they all agree that there's this very rapid drop, and within uncertainties, the inflection point here is the same. So this suggests that, at least from QCD, the chiral crossover and deconfinement appear in the same narrow temperature range. Now, coming to experimental observables, let's first look at hadron yields. And this is a plot that I think many of you have seen. This is still the best we can say right now at the LHC about the production of hadrons and nuclei. So what you see are the points, the red and green points are the experimental yields for particles and antiparticles from pions, kaons, and so on to the omega. And then we have here nuclei, deuterons, helium-3, hypertriton, helium-4. And what you see is that compared to a statistical approach, a grand canonical statistical ensemble, these are the solid blue lines. This is in excellent agreement. In fact, the reduced chi-squared of the fit, you see here data over model, this is 1.0. And this covers 9 orders of magnitude. So there are 2 points I will comment on. The one is you see here that for all of these matter and antimatter are produced in equal portions. And the other thing which we could come back in the discussion, but I think there have already been in other talks, even rather fragile objects, the deuteron is bound by 2 MeV, in the hypertriton, the lambda is bound by just in the 100 keV range. Even very fragile objects follow the same systematics. Now, an important step a couple of years ago was to introduce the effect of interactions going beyond a mere Breit-Wigner distribution. So this was introduced by Brockman-Loh and collaborators and goes back to a very old realization, namely that interactions among hadrons modify the density of states, and one can take the S-matrix formulation of statistical mechanics, in this case to the first term in the virial expansion, and then the thermal yield of, for instance, a pion-nucleon interaction channel, or call it resonance with mass m, spin j and isospin I, would just be given by this double integral, where the last term here, this is the familiar statistical ensemble characterized by temperature and the chemical potential. And then here is the modification due to interactions, and there is this term B Ji of m, which is nothing but the derivative of the phase shift in a channel with spin or total angular momentum J and isospin I with respect to the mass. And these are measured. Yeah? Here we have very good pion-nucleon scattering data. And what I show you in this lower left plot is the George Washington University site phase shift analysis. This is already the derivatives, and you see here the various contributions stashed and lines and colored lines and so on. And then in black you have the sum. And what is certainly noteworthy here is that not all contributions are positive, and there are continuum contributions and there are resonant contributions. And so it's clear that the total effect of this cannot be captured by just taking widths. In fact, it turns out that the overall effect of taking this integral is a repulsive interaction, and that means a reduction in the proton yield by 17%. If you also try to go to the next term, namely the pi-pi-n interaction. So you see here that the proton yield is reduced actually from the dashed line here to the black dot, so by 17%. Now, the challenge for the future is to go beyond the proton. Now, we know, of course, that the proton-pion interaction is special because the cross-section is huge. So even the isospin average cross-section at 140 MeV is something like 65 millibarn. So clearly to take this into account is the most important, but one can of course ask, what about hyperons? And here the situation is more difficult because there are several elastic and quasi-elastic 2- and 3-body channels that open simultaneously. And so what people have done, in particular Pogman-Loh, Peter Petretsky, Fernandez Ramirez. They use an existing coupled channel model for this case, and they find for the lambda general attraction. And this is in fact also in line with what people concluded from an analysis in lattice QCD of the susceptible baryon strangeness susceptibility. So this means an increase in the lambda yield. However, the uncertainty here is still, in the systematic uncertainty, is still very large due to poorly constrained partial wave analysis. So here there is really a need for more data. It's not clear where these data could come from, but they are needed. What has been discussed for a while in the community is the sensitivity of these thermal analyses to a possibly incomplete hadron spectrum. And so an exercise we did in 2 bachelor theses is that we went to lattice QCD and we took all the n stars and deltas that are predicted but not discovered experimentally, in total 180, and we took also all the lambda stars, sigma stars, and so on, and there are even more, there are 305. And we also took mesons from a relativistic quark model. There the number is much smaller. And so we looked what is the effect if we just introduce these states. And if we introduce them and do nothing else, but again, just fit the Ali's data, then we find that the temperature drops by 4 or 5 MeV and the chi-squared becomes awful. It goes from 1 to something like 8. So it's a terrible fit. And so this is adding successively the states, and you see. Now, when introducing, however, the S-matrix correction, that is the open points and the dashed lines, what you see is that the result comes back more or less to what it was before, very closely. So the lesson here, and the chi-squared stays at 1. Yeah? So the lesson here is that the additional baryon states, 500 in total or so, should not be considered as simple resonances adding to the proton yields. Presumably they are broad, non-resonant, with partly negative contributions. And so my summary here is all physics is contained in the S-matrix because all of the quantum numbers of the added states are in fact included in the measured pion-nucleon phase shifts. And so that is the reason why nothing changes anymore. Now, this is what I call the benefit and curse of nuclear transparency at the LHC. What you see here is the measured antiproton to proton ratio. And this is a new result from Ali's, and you see that now the errors are very small. Yeah? This is 2%. And the best fit to the data is 0.987 or so, plus minus about 1%. Here you have the value. Yeah, and so that means that is what we mean when we say matter and antimatter are produced in equal portions at the LHC. And this is, of course, consistent with a net baryon-free central region. In fact, now this constrains mu b to 0.6 plus minus 0.1 MeV. And that, however, means that when there is a penalty factor when adding a nucleon, and that is just the Boltzmann factor, e to the minus m over t, and that is about 300. So that means for every nucleon you add, you take a hit by a factor 300 in the yield. So 300 here times 300 times 300. And that is the reason why right now everything stops at helium-4. Now that is very different if you go to lower energies, and this should be heartening for people who want to work at top HES energy, and that will also be the fair energy. For nuclei, this factor is just 24. That's why Jack Sandweiss in this experiment could measure up to mass 7, the lithium. On the other hand, for the anti-nuclei, it's 140,000, and that's why he had to stop even in a fixed target experiment with the anti-deuteron. Now, so that is our difficulty to go to larger mass numbers. The other is that there is no stable mass 5 nucleus. It is also why in the early universe nucleosynthesis ends at helium. So what we can do is illustrated here when we come to 1, 3, and 4 at the LHC, and we will sample 10 inverse nanobarn. So there we expect to do helium-3 hyperhelium, helium-4 really as a function of centrality and therefore as a function of the source size, which should elucidate the production mechanism. We should really get a spectrum of helium-4. Also, the next hypernuclei, hydrogen-4 and hyperhelium-4, should by the end of 1,4 reach the 5 sigma level. Now, coming to yet another big improvement would be if ALICE 3 would take up operation in LHC runs 5 and 6. And then also hyperhelium-4 certainly is in reach, but also the first mass 5 hypernucleus, of which the antinucleus has not yet been discovered. It has a mass as expected for the omega CCC. And in fact, also mass number 6 should become accessible. Lithium-6 certainly, maybe helium-6, lightest halonucleus. And I think what one can address here is whether hadronization, looking over such a huge range and then also taking centrality dependent spectra, is this really governed by mass and quantum numbers only, as the simple picture I showed you suggests, or is there more to it? And I think it just needs more data to answer this. Now, this is the putting all what we have learned from the hadron yields into perspective in terms of the phase diagram of strongly interacting matter. And you see the data points, the LHC, and then RIG, SPS, AGS, even this data here. And the green and turquoise very narrow bands are the results from lattice QCD, the 2 collaborations that I showed you before. And what you see is that certainly from top SPS energy on, the experimental data delineate the chiral crossover temperature. Now, why this happens, I think still my best suggestion is what we worked out in this paper with Christoph Wetterich in 2004, namely that close to the pseudocritical temperature, the densities go from very high to very low over very few MeV, and therefore a very short time. And when the densities are very high, then of course you have a phenomenon that is also known as critical opalescence, that many body processes become very important. The rate for even 5 body interactions is such that it brings strangeness into equilibrium in a few Fermi over C. But then when the temperature is 5 MeV lower, everything becomes incredibly slow and takes forever. And I should say this rapid change in density is, of course, exactly driven by not only the T to the 4 dependence, but the rapid change of degrees of freedom due to the phase conversion. Okay, now, of course, people have wondered for a long time whether this approach applies also to smaller systems. And this is, I think, our most comprehensive set of data we have from the LHC for the production of pions, kaons, proton, lambda, cascade, omega as a function of multiplicity or a function of system size. And so here we are central lead-lead collisions at the full LHC energies, and then we have more peripheral collisions. We have in here proton-lead collisions, and then eventually high multiplicity PP collisions and minimum bias PP collisions. And what you see is this is work from Jean Clément and collaborators, is that one can completely account for these data by going from a grand canonical to a canonical approach, and by taking a prescription for the canonical volume that makes it actually larger than the volume of the fireball that is considered. So they consider the fireball volume of 1 unit of rapidity, and then they make VC larger, and you see that this captures the systems where the canonical suppression is large and the volumes are taken equal. This is not reproducing the data. So I think what we see here is a transition from canonical to grand canonical thermodynamics, and that accounts for all of the data. Now, since the yields of hadrons appear to be in local equilibrium at the crossover transition at 156.5 MeV and mu b equals 0, it makes sense to also study the fluctuations of these quantities and compare them to the fluctuation measure we have in lattice QCD, and these are the quark number susceptibilities. So it was recognized some years ago that these susceptibilities, which are the derivatives of the pressure with respect to a reduced baryon chemical potential, can be equated to the cumulants of the net charge distributions with a normalization factor that contains the volume and the temperature. And so this should give insight then into the nature of the chiral phase transition. Now at LHC, we are slowly working our way up. We have looked at the second order cumulants for baryons and also for lambdas. And what I show you here is the second order cumulant divided by the mean number of protons plus antiprotons as a function of the rapidity interval over which the analysis is done. And so if these were just independent Poissonian fluctuations, then you would expect in a grand canonical ensemble that these two are equal, and therefore the ratio is unity. But you see that there's a systematic and continuous decrease as the interval is opening up. And we interpret this as the evidence for baryon number conservation. And so the question is, can we find what the correlation length is for over which protons and antiprotons are correlated in rapidity? And so here then we go to a canonical ensemble, and we introduce, we sample proton and antiproton rapidity distributions and introduce correlations over some length scale, introducing the metropolis method. Actually, this was nicely discussed by Anna Rustamov in his talk in Krakow. And we obtain the correlation coefficient, which is the covariance of the two rapidities of the proton and the antiproton divided by the product of the widths. And the number that is consistent with the data is this red line, which is in fact a very small o, 0.10. And if you translate this into length in rapidity, then this is plus minus 6 units. So this is a large fraction of the entire rapidity gap. and calls into question, for instance, baryon formation by string fragmentation. I show here the black line is hygiene, where you have this is dominated by string fragmentation, and here this delta Y is plus minus 0.8, 0.9 units. Now, the future will be to go to higher order correlations. We are just about to publish the third order correlation and are analyzing the fourth order. But things become interesting when one goes to sixth order or higher, because then singular term in the pressure becomes dominating. And what you see here is both in the chiral model calculation and also in lattice QCD or in FRG, you see that this sixth order cumulant divided by the second order cumulant is even changing sign. So it's not plus 1.0 anymore, but it becomes negative. And that it becomes negative, I think has to do with the O4 criticality. At least in lattice QCD, this can be linked. And so if we measure the negative sixth order cumulant, then this is something where we can really constrain the nature of the phase transition. And this should be statistics-wise, should be possible with 1, 3, and 4 data. Experimentally, this is a tremendously difficult measurement because your control and knowledge of the efficiency enters in the 6th power, and even very tiny effects. I think our colleagues at RIC, I'm looking at Nu and Xiao Feng, can tell how difficult this is. So this will be driven by our ability to control the systematics. Now, in ALICE 3, we can extend this into the charm sector. And the first obvious thing that would be extremely interesting is if we can constrain the charm anti-charm correlation lengths and come to a similar statement whether charm is conserved locally or also over very long distances. Now, let me next turn to the charm sector in terms of hadron formation. So the idea many of you have heard many times, because we proposed this in 2000, and then we had to be very, very patient. So if charm quarks thermalize, or let's say the other way around, if the plasma screens the charmonia as suggested by Satz and Matsui, then the charm quarks remain in the fireball. And if they thermalize, charmonium production will at the latest take place at the phase bar. Quarks and anti-charm quarks that were initially not correlated can form charmonia. So this requires deconfinement. Technically, we assume that all charm is produced in initial hard scatterings, and this is at a full LHC energy still a good assumption. So the only input that is needed is a measurement of the CC bar production cross-section. And then the hadronization at the pseudo-critical temperature follows the grand canonical statistical model with the same parameters as we have for the light valence quarks. And to introduce this charm conservation, this technically leads to a balance equation that all charm quarks that are produced directly have to find themselves into charmed hadrons in the end. And this equation can only be fulfilled if there's a fugacity introduced. This is not a free parameter. There's one value for which this equation is fulfilled. And this fugacity comes in linearly for hadrons that have one charm quark. It comes in quadratically for charmonia, but also for cascades in C and so on. Now, what evidence do we have for charm quark thermalization? We have at the LHC, and this is also largely observed at RIC, strong charmed hadron elliptic flow and energy loss. So you see here the RAA in this case for reconstructed D mesons and D stars and taking the average, and you see here this very strong suppression by a factor 5 or so, very similar to what we see for pions. And you see V2 elliptic flow that is very significant, close to 0.2. This is for 30 to 50% centrality. And now there is a very active community modeling this. And the input for transport models to describe these data is charm quark spatial diffusion coefficient. And if we take here the models that in some quality measured by a reduced chi-square describe the data, then we find that 2 pi times the spatial diffusion coefficient is bracketed between the values 1.5 and 4.5, which at TC translates into a kinetic equilibration time on the order of a few Fermi. Lattice QCD has also made tremendous progress in the last 7 years since the first publication on this subject. And what I show you here is this is the status that was shown at Quark Matter, and it is still called preliminary by the authors. And this here again, the spatial diffusion coefficient is obtained from the gradient flow in color electric 2-point, the color electric 2-point function to leading order in 1/m expansion. And then again, one can compute kinetic equilibration time. So far, this has mostly been done in quenched QCD, and these are now the first attempts to do this in full QCD. I think there's a consistent picture emerging. These are results for 4 temperatures that point to a short kinetic equilibration time. So there's a consistent picture that charm quarks can thermalize in the quark-gluon plasma. Now the charm cross-section that is needed as input is very difficult to measure, because you have to measure basically all charm hadrons down to 0 PT to get the total charm cross-section. And we have recently managed to do this in proton-proton collisions, and there was a surprise, namely that the fragmentation into lambda c appears to be a factor 4 increased as compared to what was known for many years from E+, E- and also EP collisions from here. So these are the data, and you see here the D mesons, the DS. Here you see the lambda c, the cascade c, and the D star is of course contained in the D0. That's why there's this dashed line in between here. And the salient feature is this very strong increase of the lambda c. Since these are fragmentation fractions, if the lambda c goes up, of course the D has to go down. But I should say the D measurement in itself is completely consistent with what would have been expected. It's only that there are more charmed baryons. Now, some Pythia tunes with color reconnections can reproduce the lambda c, but not the data for the cascade c, and also a statistical model which about doubles the charmed baryon states by taking also states that are predicted in a relativistic quark model, or they are also predicted in lattice QCD, although at different excitation energies, and increasing the temperature to 270 MeV. If you do that, you can reproduce the lambda c. And I will come back to this question on whether these charmed states exist or not. But here I really would like to say unfortunately, among the many newly discovered states with heavy quarks, charm and beauty quarks, there are only 7 charm baryons, and 4 of those are omega Cs, and there's only 2 lambda Cs that were discovered. So right now we have no experimental evidence for doubling the charm baryon states. Now there is a puzzle though, and that is that LHCb, which measures also PP and P-lead collisions at forward rapidity, sees much smaller, if any, enhancement. So you see here in blue and black the Alice data, and then here in pink you see LHCb, and here in red you see LHCb, and there is a significant discrepancy that certainly needs to be clarified. Now, we had at Quark Matter in Krakow some new results that were shown in the talk of Benjamin Audurier, and they measured now, they showed results for peripheral lead-lead collisions. So you see here, these are the, I think they have 3 centrality bins that are the most peripheral 70% of the cross section. But you see that the data are still lower than what we measure in PP and P-lead in Alice. And I think for me, it would be very surprising if there should be such a rapidity, if this is a rapidity dependent effect, because I don't see why fragmentation should depend on rapidity. So I think here still we need more experimental data. Now, to go from PP cross-section to lead-lead, there is still a big step, and these are nuclear effects, initial state nuclear effects. And here the RIC and LHC data strongly constrain the nuclear gluon distribution function in the range 10 to the minus 1 down to 10 to the minus 5. And I show you here, this is something that just went on the archive after Quark Matter. This is the gluon distribution in lead over the gluon distribution in the proton that comes from a fit by the CTEC collaboration, and that fit includes all of the data from the LHC. So not only charged hadrons and Ws and Cs, but in particular heavy flavor data. And the heavy flavor data really make this very wide band shrink to the red band. And you see that, for instance, this very well reproduces, these are in this case LHCb J-psi data at this is the lead direction, this is the proton direction, and this is D-meson production, and you see that this suppression here, this really comes from the modified gluon distribution function. If we take this at mid-rapidity, then this RP lead would be 0.73, and then if we go to lead-lead, of course, then you have to take this factor for every nucleus, and then it would mean a suppression due to shadowing by nearly a factor 2, 0.53 plus minus 0.097. And this is in fact also supported by the J-psi yield that is measured in photoproduction at the LHC. So in the past, what we used in our statistical hadronization approach is a suppression that is completely consistent with this. But some colleagues have recently propagated that the effect should be very minor, maybe 10% or so. I think this is not substantiated by the most recent fit of the nuclear gluon distribution function. This is a very significant effect in the X range that we are sensitive to. Now, so what we want to do is Recently, there was a first D0 measurement in ALICE inlet lead collisions down to 0 PT. This was really very hard work, and there was the NDY measured here, and you see the errors are still not very small, but also not very bad. And so what we would like to do is to come away from the uncertainties going from PP, lead to lead. That is that we base our charm cross-section on this measured D-meson yield. Now, since we have not yet measured lambda C's in lead collisions down to very small PT, we assume a fragmentation like we have it in the statistical hadronization model, and that would lead to a charm cross-section or the multiplicity of CC bars per unit rapidity of 13.7 plus or minus 2. And we use this from now on as the basis for predictions for lead collisions. As an aside comment, this is slightly larger, 8.8%, than the estimate we used in the past 6-7 years. But it has a reduced uncertainty. The uncertainty is reduced from 1/3 to 15%. Now, the outlook is that in runs 3 and 4, it is really one of the most important goals in ALICE to measure with the upgraded detector, where we can take lead collisions at 50 kilohertz to make a precision measurement of all singly charmed hadrons down to PT equals 0. We have much improved vortexing capabilities also with the new inner tracking system. So this is one of the very important deliverables of ALICE in runs 3 and 4. The status right now is these are the experimental data. This is J-psi measured at forward rapidity, at mid rapidity. Very soon there will be a paper that has more precise data, but it is not yet out. So I can only show you what we have published so far. And in blue, you have the RIG results at the corresponding rapidities. And it is clear that at the LHC don't see a melting scenario, but we see a very significant increase. And I think this is the single most qualitatively different result between RIG and LHC. Taking the charm cross-section in lead that I just showed you, and otherwise the parameters as we have them for the statistical hadronization of up, down, and strange, we get the solid black line at forward and mid rapidity, and this is the uncertainty band that has shrunk a bit, but it is still limited by the knowledge of the charm cross-section. So here one would say so far so good, perfect agreement, but the errors must get smaller. If we put in the plot I showed you in the beginning, the J-psi, it sits here. The mass is similar to hypertriton. The yield is enhanced by about a factor 1,000, and that comes about just because the charm cross-section is large. And this means that this GC factor enhances just the charm conservation in the fireball, enhances the J-psi by 31 squared, which is pretty much 1,000. We have, for the first time now, a measurement for the Psi2S, and these are the results in red from ALICE that were shown at quark matter, compared to the blue points that we had from NA50. And I still remember a discussion, a talk by Michel Gonard at the International Nuclear Physics Conference in Göteborg 16 years ago or so, where he said nobody at the collider would ever measure Psi2S with a precision coming close to what was done in fixed target. So I think we are not yet there. The error is still larger, but it is largely driven by the statistical error and the difficulty to extract a very small signal. So I think in the next years, we will do a lot better than this still. And we will also have measurements at mid-rapidity where we can measure the Psi2S with better mass resolution, and therefore the significance increases. Now, the surprise here is that for the statistical model, this is basically a Boltzmann factor that is just driven by the mass difference between the Psi2S and the J psi. And what we get are these dashed orange lines. So they perfectly account for the data at the SPS. They are, at least for the most central bin, below our first results from ALICE. However, if you compute the significance here, this is 1.8 sigma. And I will not get upset about the 1 sigma effect. We had 3 sigma effects at lab that went away. So I think, we should wait. However, while we are waiting, I should reiterate, in the statistical thermal model, there is little room to accommodate such values, because if we want to increase this, then we either need a larger common freeze-out temperature, or we need, or if we just vary it for the Psi2S, we would need a larger temperature for the Psi2S than for the J psi. And certainly, if you look at what is known about the radius, we all think the opposite. If anything, the opposite is the case. So I think for us, there's very little room to maneuver here, unless the temperature would be a lot higher for charm deconfinement. Now, what do we need to clarify this? We need higher precision Psi2S data. And of course, it would be fantastic to have a third particle, because then just from the charmonium sector, we could fit a temperature and we could obtain a deconfinement temperature. Now, the chi sub c is very difficult to measure. We will, of course, give it a try in runs 3 and 4, and we are also working on the performance in ALICE 3. But because of the emission of a relatively low energy photon, 400 MeV in the rest system of the chi sub c, this is very difficult. Now, for spectra, I want to be relatively brief, because there's not much that is very new. The approach we took for spectra of charmonia, and I will also show you open charm in a few slides, is that we said if we have deconfined quarks that thermalize, then they will also have the flow that the plasma exhibits. And if we take the flow at the pseudo-critical temperature where they hadronize, this should give us a spectrum. And so what we did is we took the 3+1D music simulation and looked at the velocity profile at 156.5 MeV. And then we took this into a blast wave spectral shape. This is not the last word. We are starting, we have put the J psi directly into the hydro, but there are still some technical problems. But what you see is that at low and moderate PT, this approach, which has no free parameters, accounts for the experimental data. At the same time, it is clear when we come to 5 GeV and beyond, there is an additional component. In our simple approach, we only have the corona, where the densities in one of the 2 nuclei fall below 10% of the nuclear density. We just take the PP cross-section and also the PP spectrum, and you see that this is sort of the right slope, but there's a significant factor missing. So clearly at higher PT, there is an additional source of J psi beyond the corona of the nuclei. A very new data that we just put on the archive for quark matter is a polarization of the J psi relative to the event plane. And what you see here is the coefficient for the polarization as a function of PT for two different centralities. And there is a very clear signal observed by Alice. It tends to increase going to lower PT, and it reaches 3.9 sigma here for the lowest PT bin. Now, this makes it unlikely that this is due to the initial magnetic field, because then I don't see why this would increase for low PT. However, I find it very interesting to think about a link to vorticity and spin-orbit coupling that sort of aligns maybe the charm quarks in the plasma and then leads to an alignment of the J psi. But here really some work would be, some theoretical work would be appreciated. Now, coming to open charm, this is something we have been dreaming about for 20 years, actually 22 years, namely to get away from what was at that time the normalization to Drell-Yan, and what is now the normalization to PP by looking at RAA. The natural normalization is to look at the ratio of D0 to charmonia. And here you see for the first time experimental data. We have measured this in ALICE at two centralities, and the blue band is what we get with our current charm cross-section in the statistical hadronization model. So for central collisions, this is about a factor 50, and this is exactly what we see in the experimental data. And so this means the J psi relative to the D0 falls into place naturally and with a much increased precision that is not hindered by that much by the unknown charm cross-section. Now, going to D mesons, or generally charmed hadrons and spectra, the huge additional difficulty is that feeding due to strong decays becomes very important. In fact, you see here that D0 about quadruples if you take strong decays into account. The lambda C even increases 5-fold. And of course, in the statistical model, we have always considered the feeding. But if you now want to compute the spectrum, you have to take a hydro-inspired spectrum. And so taking again this music plus blast wave, and then let the particles decay. And we did this together with Alexas Matsiliauskas and Vytautas Vislavicius, and you see that this does significantly modify the spectral shape, taking this into account. Doing this, you see, for the D meson is very similar message in the end to what I showed you for charmonia, namely that up to about 2 times the mass or so, this can account quantitatively for the data, but for high PT, there is an additional component. There's more to it, as we would have expected. Now, ratios of D mesons here all normalized to the D0, D plus to D0, D star to D0, D sub S, and here the lambda C. We have experimental data. They go not yet to 0 PT, so we can only integrate the PT, compare PT differential. Somebody wanted to say something. Okay, so you see this is well within expectations. The large error comes because the PP spectrum is not yet measured precisely enough. And so this will improve over time. Now, I told you before that there was a successful attempt by Alfrab and Minier to reproduce the lambda C yield in PP collisions by doubling the charmed baryons. And so we looked what effect this would have in our statistical model if we do this, although there is no experimental evidence right now. And if we do this, then I go back and forth, you see that the lambda C, certainly within errors, now comes close to the experimental data. So the lambda C increases by a factor 2.15. The D meson is practically unchanged, and the total charm cross-section would go up by 18%. So these are things that will be measured in ALICE in 3 and 4, and we will see whether such an approach is justified. This is looking to the far future now, to ALICE 3. If we take this increase by a factor GC for every charm quark, then we can project predicted yields for charmed hadrons as a function of mass for singly charmed hadrons, and in fact here also charmed nuclei, the C deuteron or the C triton. Here you have doubly charmed charmonia, but also omega CC, cascade CC, and here would be triply charmed, and you get a factor 30 every time. So that means these yields become really large, and these particles should be measurable with ALICE 3. So if the omega CCC at this mass exists and it decays as one could deduce from known symmetries, we should be able to see this in ALICE 3. In fact, also exotica like the tetraquark candidate, the Chi-C1 or the X3872 should be measurable, and there's a very specific prediction for how the spectrum should look like. In fact, also the TCC plus should come within reach. You see here a simulation that is, I think, for the anti-C deuteron. If we take the full luminosity that we expect right now in ALICE 3 that we have put into the letter of intent, so that if the particle exists and if it is in mass where we now think it should be, there should be very clear a signal. Okay, should I end or should I spend 2 minutes on beauty? We can do it either way, but I can also, I think I have only 2 minutes left.
Go ahead, Johanna.
Okay, so the first thing I want to ask, is there evidence that beauty thermalizes? And these are new data we have from ALICE, just put onto the archive in February for the RAA of D0. And in red, you see prompt D0, and in blue, you see D0 coming from BTKs, non-prompt D0. And you see that certainly it is very strongly suppressed, but the suppression is about a factor 2. The RAA is about a factor 2 above the one for charm quarks. And similarly, if you look at V2, this is now for electrons that come from B decaying to charm and then to decaying semi-leptonically. And you see that there is a very significant non-zero V2. However, if you remember what I showed you before for the D mesons, it is up here. So there's a large V2, but it is significantly less than for D mesons. And so from this, I would say there's an indication that beauty quarks thermalize only partly. And if we now think about such a statistical harmonization approach, it should apply only to the thermalized fraction. So this is what we get if we just take the B cross-section and we ignore that maybe only part is thermalized, and we compute what we expect for the RAA of the Y1s, Y2s, Y3s, and we do this at forward and with rapidity. So indeed, the assumption of fully thermalized B quarks fails to reproduce the Y1s. We are above the data by a factor 2 to 3. However, the GB, this fugacity that was a factor 30 for the charm, is 10 to the 9. So, of course, for the Y, and it's 10 to the 9 squared, we scale the thermal yield by 10 to the 18. And considering this, I find a factor 2 to 3 not so bad. So maybe there is something to this picture. Now, of course, we can play a bit and we can say, what if 50% of the B quarks thermalize, or what if 30% of the B quarks thermalize? And you see that then we come close to the data. Yeah. So now, how could this be, and what could the physics behind this be? So my picture would be that the B quarks do not, the interaction is screened at the high temperature, high initial temperature at the LHC, and duty hadrons do not form before the quark-gluon plasma forms. The interaction is screened in the plasma. We have this strongly coupled system, and certainly the B quarks interact. So even if they don't fully thermalize, maybe that interaction is enough to break the correlation, so that the ones that don't thermalize also don't form Ys, but they go in the end to open QT. And the ones that are thermalized form, for instance, Ys. So that would be one possible scenario. Now, let me then conclude with this, with very few sentences. So the yields of hadrons and nuclei with UDS valence quarks delineate at high energy the pseudo-critical temperature for the chiral phase transition. The net charge fluctuations at high order should be sensitive to the nature of the phase transition, and we are working hard to get there experimentally. The yields of hadrons with open and hidden charm are characteristic for hadronization of deconfined charm quarks, and the upgraded experiments in LHC runs 3 and 4, and certainly ALICE 3 in runs 5 and 6 will allow to address many of the open questions in a qualitatively new manner. So let me finish by thanking my collaborators, some of them over many, many years, and some of them recent nature. Thank you very much.
Thank you very much, Johanna, for this very nice talk, and also very clear. So we got a few questions from the chat, but let me start with Edward, who has raised his hand.
Hi, Johanna, again. You hear me, right?
Yeah.
It's a small question about some issue we discussed like 10 years ago about charm, now about beauty. When people compare or calculate hydro prediction for spectra of these beauty hadrons, they just do the same blast wave and distribution like for any other hadron, right? However, this B, as you said, have this huge fugacity, large chemical potential, and assumption that this is homogeneous over fireball is not justified. It should be much more in the center than at the edge of fireball, because they're produced differently. Yes, I'm curious whether anybody account for that.
Yeah, no, we have discussed this many times, and of course the production should basically follow the radial profile of the number of binary collisions.
Of binary collisions, so it's
Yeah, of
way
binary collisions, so this is more peaked in the center.
right. That's my
However,
point.
I think for charm,
Yeah, for
the
charm,
fact
it
that
turned
the
out
charm
to be
was
small.
normalized, yeah, I think there the effect will be small. For beauty, indeed, it could be that this stems from a smaller local region.
Right.
And then right now, I don't have a good idea how to implement
Well,
this.
some Hydra people should do it, but if fugacity is 1,000, it's very hard to believe it's homogeneous over the whole fireball. It should be more central. Anyway, it's something to be done. It's clear what to do.
Yeah, it would need a real dynamical model to produce or to follow the B quarks and to have some. Now, looking, the lattice people have in fact computed also the spatial diffusion coefficient for beauty. It only exists in quenched QCD, but there it is even smaller than the one for charm.
Right, so you may think they remain in that hydra cell where they're produced more or less.
No,
Diffusion is small.
I think the plot, I changed the plot yesterday, and the one that I have here does not show this anymore. No, I went too far. Sorry. Now we're getting there. Okay, so the value, so this is 2 pi TD for the charm quark, and you see that this is D is proportional to the kinetic equilibration time. The value at 1.5 TC for the B quark is where the hand is right now.
Mm-hmm.
So the question is whether we can believe this.
But then for B, it is divided by n, right?
In PQCD, the value was huge. Yeah, it is divided by n. Yeah, okay. We should, yeah, we have to be fair. There's factor 3 or 4.
Mm-hmm.
And yeah, then all bets are, well, it could still be, it could still be 5, it could still be 5, 6, 7 for me, right? So it could still be the lifetime of the plasma.
No, but the question is whether they can diffuse from a center to the edge. I'm saying this fugacity at result surface cannot be homogeneous.
Yeah, so the one is, yeah, I share
it's just a small comment.
I share this feeling with you.
Okay.
Okay, so let's move on. So the next is Joachim.
Yeah, thank you, Johanna. I have actually a question. Maybe I did not fully understand. I mean that the let's say the phase shift version. I mean of the interacting hadron gas compares so well to the standard PDG with Breit-Wigner. I mean the higher resonances couple strongly to 2 pi channels, and if you basically base this on a phase shift, I think you have pi nucleon, but not, I mean, you have not 3-body interactions, right? So isn't there, I mean, how can that be that this resonances which are coupling to 2 pi, which you have in the PDG, which you take into account by a Breit-Wigner typically,
No,
then
we don't
accounted for in the phase shift case?
No, we don't do Breit-Wigner at all. So
I know, but if you do, I mean, if you just take the PDG values, you have the resonances, higher lying baryonic resonances, which have a dominant 2 pi decay channel, right?
Then I get disastrous results, right? This is what I showed you here. If I take all these additional states, then all hell breaks loose. And if we do it only for the known states, then we had this old proton puzzle where the yield is off by close to 50%. So the reduced chi-squared is 2. So if we do just Breit-Wigner distributions, it does not reproduce the data. While taking the phase shifts and taking we estimated what the pi n is only from lattice QCD. What the effect of pi yeah.
But still, I think in the standard, I mean, the typical particle list which is used in the hadronic, in this statistical hadronization model,
does not reproduce the photons. It does not reproduce the photons. So this was the single point that made the chi-squared for the LHC data, the reduced chi-squared 2.0 instead of 1.0.
I know that it happened like this.
We only get this type of fit when we do the phase shift correction for the interactions. When we do Breit-Wigner, the fit is, this has bothered us so long, and that's why we did this exercise with taking all these additional states. That was in parallel to Bockmann-Loh developing the phase shift analysis. We said, let's brute force, just assume there are many more states, but it makes it worse. If you assume there are naive Breit-Wigner resonances, it's a disaster.
Yeah, no, I understand, but still it's surprising that with basically only pi nucleon, you get everything you need, and that there are not these other resonances which are there, not contributing to this business. Yeah.
Okay. With pi nucleon alone would bring me to a 24% reduction, and then adding the pi n goes to back to 17%. So one third of the effect.
Okay, then
that is reduced. So there is an effect.
Okay, good. Then it's fine. Thanks.
Mm-hmm.
All right. So next is Bernd.
Hi, Johanna. I have first a quick comment on Edward's comment, actually. It's not quite as simple as that, because the shadowing of the gluon distribution in nuclei is also impact parameter dependent. And so you get more suppression of the gluon distribution in the center of the nucleus than at the edge, which works exactly opposite to the increase in the binary condition number. And I've not seen an actual calculation that explores this, but I would expect that at least for charm, where the suppression of the nuclear modification of the gluon distribution is quite significant, this might wipe out much of the effect of actually the difference between binary collisions and participant numbers. But
but for these transversity distributions, we really need more data. Right now, for the nuclei, that's not enough data, but the effect, the expected effect is exactly what you are saying.
Yeah, so this might partially offset that. The question that I have is, when you think about this factor of 30 or so enhancement of D meson production over the naive thermal model without fugacity at the LHC, then obviously the reaction rate in the hadronic state of DD bar or DD bar star is a factor 1,000 enhanced. And the reaction of two D mesons of DD bar star to J psi is highly exothermal. And I wonder whether anyone has actually looked at the question whether you could not establish the equilibrium, the thermal equilibrium in the hadronic phase if you have such a high fugacity for D mesons.
I think the densities are still not very large. So we are at 1.7 in GeV, and that then going up, this brings us to densities that are comparable to, say, the phi meson, not lower than that, somewhere the cascade or so. But yeah, we can think about that. I think that
it would be
still small, and in particular, if you go below TC, that was what I was saying initially. What we worked out, the rates we worked out in this paper with Christoph Wetterich, the densities very quickly become very low. Right? These are densities at TC. If you go 5 MeV lower, I mean, this all it falls apart.
Yeah, I mean, I know that, of course, we made this argument for strangeness, right? For the multi-strange hadrons. But the situation here is a little bit different because the reaction is highly exothermal and therefore has a very large cross-section potentially, right? So I think it would be worthwhile looking into this. Also, if the reaction, I mean, once you have a pair of d mesons and the light quarks annihilate, the charm quarks have to go somewhere. But they have to go into some state of a charm anti-charm. And this could lead to a slightly off-thermal enhancement of the psi2s, right? Because on average, the CC bar will not be very close together if two d mesons have a light quark annihilation. And that would favor a larger state recombination rather than a very tight state. So I could imagine that this actually could be potentially a scenario in which you get an enhancement of psi2s.
But the fact that phase space is large for DD bar going to J psi does not mean the matrix element is large. So I don't know about the cross section.
Yeah, but it's a light quark matrix element, right? Because they have to form a pi meson or something.
What do you want to do? A few millibar?
Well, I don't know. I mean, it's something that it would be worthwhile looking into. Yeah. Is all I'm saying.
Yeah.
If you want to make the case that this is a proof of deconfinement.
Yeah.
Okay, thank you, Bernd. And so we have now Kaija Sun.
Yes. Hello, can you hear me?
Yes, we can. Go ahead.
Hi, Johanna. Thank you very much for a nice talk. You mentioned that the statistical hadronization model can describe both ordinary hadrons as well as deuterons and helium-3 at the LHC energies. However, it has recently been found that in the statistical hadronization model, there is an overestimation on the triton and helium-3 yields at collision energy are less than 200 GeV. So do you consider this as a puzzle, or do you have some explanation or comment on that?
Well, I have seen only arguments being made about ratios and not about absolute yields. So if we have absolute yields, we can compare them. But if you just look at ratios and we do this coalescence type arguments, that is something different. And we do not know if the ratio is explained, does not mean the two individual values are explained.
The yields, not only the ratio, but also the yields, not only of the RIC BS energies, but also from measurements by NA49 collaboration. There are many data points at collision energy lower than 200 GeV.
Yeah, I looked at the NA49 data. I started to do this actually for a meeting in Cape Town that Frank Clemens was organizing in 2010. I looked at all of the existing data from NA49, and at that point with Rick, it was really just starting, and there was the hypertriton, and the NA49 data within the errors, that there's no problem at all. In fact, also the HES data, Jack Sandrice data going out to Mars 7 is all fine.
So you mean there's no discrepancy there?
I'm not saying that. I'm saying just looking at ratios is for me not yet enough. But the more data you can collect, the tougher it will be for us. That is very clear.
All right.
So we need to take all data very seriously. Of course, at very low energies, we are in a different ballpark, because then eventually fragmentation will become a major difficulty. But that's much, much lower energies.
All right. So yeah, I just want to mention that the at BS energies, the D2P ratio is well described by the statistical hadronization model already, but the helium-3 over proton ratio is far below the statistical model, statistical hadronization model prediction. That's what I found in the literature. Yeah. So.
Okay, thank you, Keija. So Peter, would you like to make a comment on
this? Just a brief comment. There is a very funny situation indeed, that the NE49 data at full SPS energy are perfectly consistent with the standard statistical hadronization model predictions. The recent publication from NE49 at lower energies are indeed different. Not so much different, but they are different. Now, I have no idea how this can be that there is a change in these ratios as a function of energy. So this is an open question. I should also say, of course, that one has to take into account also the S matrix correction for the helium-3 and triton. Incidentally, the triton to helium-3 ratio is poorly measured and not, I think, does also not lead to a reasonable value at the moment. That's another open question, but I think there is something like 30% or so for helium-3 correction from the S matrix correction, which we did not use at LHC because we had 30% uncertainties in these values when we did this calculation. If we reduce at LHC by 30%, I think it still would be very good description. So this is something one has to take into account also, because if there are fewer protons, then there are fewer helium-3. But that would indeed then lead to, and the same is true, by the way, for neutrons. So there is no difference between protons and neutrons. So you cannot change the helium-3 to triton ratio. And I don't understand the helium-3 to triton ratio, neither from STAR nor from I think, no, NE49 doesn't have triton, but not also not.
But we know from Alice how difficult it is to identify.
It's difficult to measure.
To see. Yeah.
Okay, thank you.
Okay, thank you, Peter. So we have then next is Min He. Min.
Yes. Hi, Johanna. This is Min speaking. Thanks for your very, very wonderful talk. My question is concerns the psi prime to J psi ratio. So it seems you were suggesting a higher freeze-out temperature for the psi prime, for the excited states, than J psi in order to accommodate this ratio in the statistical hadronization model. But from our point of view, this is not quite likely. For example, judging from the data of the PA data of J psi and psi prime suppression, psi prime has a significantly larger suppression in PA than J psi. But they have the common cold nuclear matter effect, right? So that means the psi prime must suffer from a larger reaction rates, inelastic reaction rates, in hadronic phase than the ground state J psi. So the psi prime may be freeze out well into the hadronic phase. That means it has a lower freeze out temperature than the J psi.
But then how do you get the yield? I'm not saying See, for both these scenarios that I mentioned here, I say they are probably unphysical, and I don't want to do this. I don't want to have a higher freeze-out temperature for the Psi2S. For me, this is completely counterintuitive.
Sure, I fully agree. Thanks.
Okay, so then the next is Anirban.
Yeah, thank you for the nice talk. And I just wanted to point out in your slide 6 where we were earlier about this proton. So there, this from 25 to going to 17%, as you said, that has the input of lattice QCD. And this matching was done exactly at the freeze-out temperature, right? 156 MeV. Now, given the fact
it was done for every point here, the whole curve, right? So we matched for each temperature.
Okay, but my point here was, so given the proton is the dominant part in the baryon charge correlation, so is it indicating really to the fact that this exercise tells us that LHC gives us correct amount of proton, which will be given by the which matches with the equilibrium QCD calculation? Is it indicating to the fact, and related way, I mean, then is it indicating to the fact also that rather than HRG, we should employ QCD as the theory to get the properties of the medium out of the data rather than HRG?
What I'm saying is in the confined phase, the statistical operator that we are using is also the statistical operator of QCD, because lattice QCD is reproducing the measured hadron spectrum, right? So of course, this pertains only to a phase where you have hadrons. The hadron resonance gas is QCD. And so what we do is we look at the contribution to the pressure for the taking into account pi n or pi n. And for the just pi n, we don't have to do this because we can look at the phase shifts, but we see that there is agreement. And for the pi n, of course, we have no experimental data, and we have to look at the difference this makes on the pressure in lattice QCD.
Yeah, and since this is in exact agreement, so basically, although I have to then double check the whether this matching was done by temperature, as you say, but even then, I think then it is just saying that chi, I mean baryon charge correlation given by the equilibrium QCD is the perfect amount which is given by the proton in LHC, right?
That is fine, but if you tell me that you want to calculate in lattice QCD how many protons we produce in a central lead collision,
we can't.
I would be very happy. Then I don't have to make.
No, that's not my point. We can't. But this exercise gives me a bridge. This exercise gives me a bridge to do that somehow.
The bridge is for me the statistical operator that is QCD. Of course, they must be related, right?
Okay, I propose
thank you.
We move on, and we also have to close soon. So we have Edward again, and then move.
Yeah, I apologize for sticking up the second time. This is a comment on Bern's comment. I actually agree with him. I just propose another view on this. Johanna, of course, remember that this is the issue of psi prime to psi. Very many years ago, I wrote a paper with Heinz Zorge that for SPS data, there was the ratio was consistent with the normal freeze-out. Now that it is at LHC it is different, as of course Johanna herself predicted. So most of the psi's and psi prime are coming from coalescence. So we studied some time ago classical Langevin dynamics. So at early time or at low energy, the dynamics is you start from J psi, it is excited up. There is a flow from J psi to higher states, etc. Here is the opposite. At freeze out, a lot of charm go down to J psi. And so there is a flow along the states downward. And if there is not enough time, so deviation from equilibrium indeed enhance psi prime and maybe psi 2 prime. So this is similar to effect which Bent mentioned.
Yeah, I remember.
Deviation from equilibrium can happen because it comes from top to bottom. And some of them are extra stuck up. That can be studied, of course, in dynamical approaches. But it is a principle, again, the same ideas you had. At low energy SPS, it was dissociation. So it was diffusion up from J psi. Now it is diffusion down to J psi.
Yeah, I understand what you mean. That's an interesting point.
Okay. Thanks.
All right, so now it's your turn.
Hi, Johanna again. Thank you for the nice talk. I have a question. I think it's on slide 12 about the nature of the transition. I remember you said the transition is about 5 MeV. I'm sorry, not this one. Then. With the phase, yes, this is the one. How do we know this 5 MeV? And do we have any experimental measurement to tell us the nature of the transition here?
No, what we did, remember what we did in the paper is we estimated rates for specific processes. For instance, 3 kaons and 2 pions making omega and an antinucleon. And then, of course, you can now change the densities according to the temperature, and you can see what happens to these rates. And then you see that within 5 Fermi, you go from, say, 5 MeV, you go from 0.2 Fermi over C to 20 Fermi over C in the time scale for equilibration. So there are orders of magnitude within a few MeV. And that's why we made the estimate that the freeze-out temperature must be within 5 MeV of the pseudo-critical temperature. Because just taking data from lattice QCD on the entropy density and the temperature dependence, right? Just saying, how do the densities in this regime scale? And then you have to, of course, assume some characteristic cross-section, which in the case, what we did is, I think, pretty safe, is we said the omega antinucleon cross-section is at the same energy above the threshold, just like the PP bar cross-section. There's no reason that PP bar going into 5 pions, if you look at the same energy, should be different from omega antiproton going into 3 kaons and 2 pions. They're both allowed as far as the strong interaction goes. And so we said, and then we take the inverse cross-section just from detailed balance and multi-particle phase space, which was nicely published by Keo Kayantia in the paper ages ago. And so then you have the rate. You have a cross-section and you need the densities that enter to the 5th power. And then we came to these time scales. Now, of course, this is a bit rough because we just look at one process and we said, let's look what is the time scale for this one process. And then it goes from very rapid to extremely slow within 5 MeV.
Okay, thank you.
Okay, so thank you very much, Johanna, again for the talk and also for the discussion. Thanks everyone to the people who have been asking questions and for participating in this meeting. And I would then turn it over to Xiaofeng. There may be some announcement for the next seminar.
No, actually, no. Thank you for everyone for participating in this very nice talk from Johanna, and also thank you for Luciano for this nice chair. Yeah, thank you very much. Yeah.
It was my pleasure to talk to those of you who I didn't see at Quark Matter. It was really fun. Thank you.
Xiaofeng and Johanna, I
Thank you.
understand that the talk will be made available at the Indico page soon, right? The presentation file.
Yes, yeah. Johanna, if you please kindly send me the slide. And if you agree, we also...
the file is not very big. I think I can even send this by email. It's only 5 megabytes.
Yes.
Mm-hmm.
Thank you.
Very good. Okay.
All right.
Okay.
Bye.
Bye.
Thank you, everyone. Bye-bye.
Bye.
Bye.